Okay, let's continue with our topic under discussion, Thevenin and Norton equivalent circuits. We stopped on this slide last week. Okay, so I use this example circuit to point out where and how we can apply, or not apply, but where and how we would need to apply Thevenin's and Norton's theorem, right? We're trying to find a specific value for a particular component, and we need to analyze the rest of the circuit to determine the optimal value for that component. And there are three parts or three quantities to determine. First one is the Thevenin resistance, Thevenin voltage, and then the Norton current. And as I've stated previously, this is not a new analysis technique. What you're doing here is you're simply taking the analysis techniques that we have learned so far, and we apply to these theorems to determine the actual voltage, the current, and the resistance. So, I kept using the word equivalent networks or equivalent circuits. The reason is, as seen by that particular component, in this example, it was R6, right? If you look at the circuit from the perspective of R6, the circuit will have a voltage and a current through that particular component that remains the same no matter what the value of that component is. Again, if you remember the example, I said R6 could take on multiple values, right? You could plug in R6 as 10 ohms, 15 ohms, 15 mega ohms, 5 kilo ohms, doesn't matter what the value for that resistor is. As long as the rest of the circuit remains the same, then the voltage across R6 and the current through R6 will always remain the same. Hence, equivalent circuit, okay? The rest of the circuit is represented by a equivalent voltage source and a resistor in series, or a equivalent current source and a resistor in parallel. And that's where the term comes from, equivalent. So again, voltage and the current through those terminals will remain the same no matter what the value of that component is. In electrical engineering, anything that supplies energy is a source. Anything that receives energy is a load. And so when I say load in here, it basically means the component that we were talking about. So in the previous circuit, R6 was the load. Okay, I think I briefly talked about this load during the first week of class, which was, well, a while ago. Anyway, so the second point is that we only study linear components and linear circuits in this class. Linear is basically resistors, resistors, ideal sources, capacitors, and inductors. Non-linear elements are basically our transistors, solid-state devices, diodes, stuff like that. In resistor, if you increase the voltage, the current would increase in direct proportion, okay? And hence it's linear. The response and the relationship between a voltage and current is linear. Hence it's a linear component. So Thevenin and Norton applies to linear circuits only. This is not something you have to worry about, again, because the only analysis we perform for Thevenin and Norton is basically on the resistive networks or resistive circuits. So it's all linear circuits. And then any one-port linear network, one port meaning a set of input or output terminals. Again, basically what we saw here in this example, out plus and minus combine, and we call this as one port. Again, when it comes to electrical engineering, we deal with larger circuits. Sometimes they have an input and then they have an output. All circuits, of course, have an input, but when we draw our schematic, we draw the sources directly within the circuit. That source, whether it's a voltage or current source, is the input to that circuit. So if we wanted to represent, we would say that this portion here is the input port to the circuit. But since there are multiple sources in there, we don't refer it to that. Okay. Anyway, two sets of terminals together will form a port. Again, those are just a couple of points. Well, actually 3 points to note, but they do not affect your analysis. Okay, just conceptual. They just talk about a little bit of the concept. Now, the next 2 slides, including this one and this one, these are the most important. These are the steps. These summarize the steps that would be required to determine the Thevenin and Norton equivalent circuits. Okay. Remember, I said you have to determine 3 independent quantities: resistance, voltage, and current. Okay. All 3 circuits, you will modify the original circuit in some way or some shape, and then you have a different circuit which you will need to analyze independently of the other 2. Again, 3 quantities: resistance, voltage, and current. So it's 3 different analyses. Okay. The results you obtain from one circuit have no bearing on the other 2 because all 3 of them are different. All 3 of them are completely different circuits. So you would take the original circuit, you would redraw that circuit 3 times. The first for resistance, well, actually it doesn't matter. I just like to teach resistance first. So I always say first for resistance, second for voltage, third for current. But you can do those in any order you want. I take resistance because that's the easiest. Okay. For resistance, what we do is, let's actually go to the next slide. For resistance, we redraw the original circuit and we reduce all the independent sources in that circuit to 0. Okay, so any independent voltage source or current source in there, we reduce them to 0. Again, it is not a new technique. You already learned this in the preceding weeks, right? Everybody should be familiar with reducing sources to 0. Replace a voltage source with a short circuit and a current source with an open circuit. Then all you have left in the circuit are a bunch of resistors. Okay. Right here, point number 8. Even though it's listed the third, I would say always start with the resistance because it would be the easiest. So you reduce all independent sources in the circuit to 0, and all you're left with in the circuit is a bunch of resistors. You find the total REQ, the total equivalent resistance at those output terminals where a component was connected. And that gives you your RTH. Okay. So the circuit in the previous example was R6, right? We removed R6 and we were analyzing from the view of R6. So you measure REQ between those terminals. And that would give you the Thevenin resistance for that circuit. Okay, that gives you the Thevenin resistance for that circuit. Now, REQ again is simply taking resistors that are in series and parallel and reducing them down to one single resistance, which is something we did at the beginning of this chapter. So again, not a new analysis technique. You're simply applying the technique to determine the Thevenin resistance. Let's take a 5-second pause. Let me know if you have any questions. Yes. No, that was going to be my next point. Yes. 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 Yeah. And we'll look at an example next page. but that's for Thevenin resistance only, RTH. So once you find RTH, keep this point in mind. You redraw the circuit 3 times, okay? So you have the original circuit. CKT is my acronym for circuit. So original circuit, you're going to redraw it 3 times. Actually, let's make it smaller. Thevenin voltage, Thevenin resistance, and Norton current. Now we know the relationship between the 3 is given by Ohm's law, but once you find the value of RTH, you forget about it and keep it on the side, because that value of RTH does not have any bearing on the circuit for Thevenin voltage or Norton current. Okay, there is no relationship other than this, which is implied after you find all the 3 values. Okay, not before. So if you're trying to find the Thevenin voltage, then the Thevenin resistance has nothing to do with it, nothing to do with the circuit. And time after time, I see students make errors, and so I always emphasize on this point. Okay, the Thevenin resistance, or any of these 3 values, have no bearing on the other two on the other 2 values. So once you find Thevenin resistance, you go back to the original circuit, and at this point, all you're doing is you're taking the original circuit and you're determining the output voltage at the terminals where R6 was connected. Okay, so again, you're trying to find the Thevenin and the Norton equivalent circuit at an open pair of terminals. So when you remove R6 from the circuit, those open pair of terminals is where you would do all of your measurements. So all you're doing for Thevenin voltage is you're going back to the original circuit and simply determining the voltage at those pair of terminals, which you can do with any technique you want. Mesh current analysis, node voltage analysis, superposition, series parallel analysis, if the circuit allows for that. Any technique that we have learned so far, you can use to determine the open circuit voltage at the output terminals. And that is what we do here. So we had the larger circuit. I'm going to put it in a sealed box. And then we had R6 connected here. I'm just using the previous example. Right, so this will still stick with out plus and out minus. These were the open terminals. All we do is we analyze the circuit and we find the voltage between these 2 terminals. It is referred to as the open circuit voltage, VOC, because the terminals are kept open. Right, you removed R6 from your circuit. Now there is nothing connected between those terminals. So open circuit, you find the voltage between those pair of terminals with a positive up top. Okay, the reference direction, the reference polarity is always plus up top and minus at the bottom, depending on the circuit. Now your answer could turn out plus or minus, that doesn't matter. But when you're analyzing for the circuit, you always find VOC with a plus on top. Again, choose any technique you want. Mesh current analysis, node voltage analysis, superposition, series parallel analysis, KVL, KCL, Ohm's law. You can apply anything you want. You find the voltage at those terminals. That is your Thevenin voltage. Again, not a new analysis technique. You're simply applying that technique to a larger network theorem. All right, questions? Any questions? Yes. There's no reference yet. Doesn't really matter. Yep, just the difference between the two. Any questions? Then the third one is mesh current, and well, not mesh current. The third one is Norton current. And for Norton current, what you're going to do is you're simply going to take the output terminals and place a short between them. Current needs a pathway to flow through. So if you want to analyze this circuit, you have to place a short circuit for the current to flow through. So I'm going to draw this out. And the current direction is always taken as going from the top to the bottom. Again, this is out plus, out minus. This is known as ISC, the short circuit current. Again, it's the same pair of terminals where R6 was connected. You're simply taking R6 out and you're placing a short circuit wire between those terminals so that current can flow through those terminals. Then we analyze the exact same circuit. Again, we analyze this. Good movie, by the way, if you've never yet seen it. There's a movie by the name of Analyze This and Analyze That. Two of them. Anyway, you analyze this circuit twice, once for open circuit voltage, second time for the short circuit current. Open circuit voltage is a Thevenin voltage, short circuit current is your Norton current. And then you can verify your answer by applying Ohm's law between the three terminals. Each circuit is different. Okay, a simple short between those terminals can change the circuit drastically. Okay, and we'll look at examples on Wednesday, and then of course it'll start making more sense. Almost out of time, but those three circuits are independent. If you take RTH and you apply it to, I don't know, to find VOC or ISC, your analysis would be incorrect. So do not do that. All three circuits are independent of each other. Okay, all three circuits are independent. So as I said, RTH is rather straightforward. So take a crack at this. All you're doing is you're trying to find the REQ between these terminals. I will go over this on Wednesday, but again, this doesn't take more than 5 minutes. You reduce all independent sources to 0, meaning voltage sources are replaced with a short, current sources are replaced with an open circuit, and you simply find REQ between the terminals. All right. So I'll stop right here. We'll pick up here again on Wednesday. Thevenin Norton homework, I have set it due for Friday. I might push it back to Saturday, depending on how much we cover on Wednesday and Friday. But at least take a look at the homework, open it up. Take a look at the questions. Superposition is due tonight, I believe, tonight. So again, 2 problems. If you've not yet done that, go ahead and do so. And let me know if you have any questions. I'll be in my office. All right. I'll see you all on Wednesday.